class. Today we will discuss on the following objectives. The first objective would be the notations of the stress, both the normal stresses and the shear stress. Thereafter we will go through some of the examples, how we can define the stress at a particular point in 3D. Thereafter we will move on to general state of a stress in two-dimensional. Stress notations or the notations of the stress. As stress is a second order tension, it is defined by one of its values and two values define its directions. So the general state of stress at a particular point, a particular value is represented by sigma, I and j. I and j are the subscript denoting a particular type of the stress. The stress can be normal stress and the shear stress, where the first subscript I represents the directions of the plane normal. So plane is always defined by its plane normal because it is constant for a particular plane. Second subscript j represents the directions of the stress. So the first subscript represents the directions of the plane normal and the second subscript j represents the directions of the stress in which it is acting. The stresses can be both the stresses, the normal stress as well as the shearing stress. Here a note has to be taken regarding that plane. We always define a plane. Over here this is a particular plane. Then this particular plane is defined by its plane normal. Plane normal is acting perpendicular to that particular plane because this is constant throughout for a particular plane. Again the similar thing, this again it is acting in the z direction, again it is acting in the z direction, again at this particular point it is acting in the z direction. So the plane is always defined by its plane normal. Normal over here means that the vector pointing perpendicular to the surface. If we consider this particular plane, then normal would be perpendicular to this surface. Similar to this, again if we have to define this particular plane, this is the plane. In that case the plane will be defined perpendicular to this surface which is acting in the y directions. Similar to this, if we are interested in finding the other plane which is this plane, again this plane will be defined by its plane normal. This is acting in this direction. Again if we consider this particular point, again this plane normal will be acting in the same directions. That is why we take or we define always a plane by its plane normal, because it is always constant irrespective of the positions which we have chosen. Again this small element is very small because we are always interested in finding the stress at a particular point. That point has to be very small. That's why the small elements we have chosen, it's very small. This means that delta x, delta y and delta z, which is the element which we have chosen, is very small. Now to define the general state of stress at a particular point, it is defined by the following matrices. So if we are interested in finding stress at a particular point, the number of components that we need to define the stress at a particular point will be altogether 9. Among these values, sigma xx, sigma yy and sigma zz are considered as the normal stresses because these are acting perpendicular to the surface which we have chosen. The next, these values sigma xy, sigma xz, sigma yz and sigma yx, sigma zx and sigma zy, these are the shearing stresses. So a particular state of a stress in 3 dimensions will have 3 values of the normal stresses, and 6 values of the shearing stresses. Among all these values of the shearing stresses, we will have 3 values which are similar to other 3 because these are the complementary shear stresses. Some of the books define the stress by different notations. Some of the books still represents the shearing stress by sigma, but some of the books represent it by the terms tau. So both these notations are equally good. Over here, the general state of the stress, the first row of this matrix represents the forces that are acting on a plane that is defined by its plane normal that is acting in the x directions. The values of the stresses are sigma xx, this is sigma xx, sigma xy, and sigma xz. The second values of the stresses that are acting on the other phase, that is the phase directed by the plane normal. This plane normal is directed in the y direction. The values of the stresses are sigma yy, which is acting in the y directions, which is the normal stress, tau yz, which is acting in the positive y directions, and tau yx, which is acting in the positive x direction. Similar to this, we have other forces that are acting on the next adjoining phase, which is the phase defined by the plane normal, which is the plane represented by 3, 4, 5, and 6. So on this particular plane, this again plane is defined by its plane normal. This plane normal is acting in the positive z directions. So the values of the stresses that are acting is sigma zz, that is acting in the positive z direction, tau zx, which is acting in the positive x directions, and tau xy, which is acting in the positive y directions. So the next questions is when we will say that the planes are positive and when we will say that the planes are negative. So in this case, the positive planes are represented by 1, 2, 3, and 4. So this plane represented by the figure 1, 2, 3, and 4 are the positive planes, one of the positive planes. The next positive plane is represented by the 2, 3, 6, and 7, which is 2, 3, 6, and 7, which represents this particular plane. Again, this is again regarded as the positive planes. The next positive plane is 3, 4, 5, and 6, which is represented by this plane 3, 4, 5, and 6. So this particular plane is also a positive planes. So what are the negative planes? The planes opposite to all these faces. Planes opposite to all these faces are the negative planes we have. So the negative planes that we have are represented by 7, 8, 5, and 6, which is 7, 8, 5, and 6. So this one is one of the negative planes. The other negative planes will be 1, 4, 5, and 8, which is 1, 4, this value 5, and this value 8. This is regarded as the negative plane. The next negative plane is represented by 1, 2, 7, and 8, which is again 1, 2, 7, and 8. So again this plane which is at the hidden portions, this plane is regarded as the negative planes. So the next questions arises, how we will define which all planes are positive planes and which all planes are the negative planes. So how to decide when stress, both in terms of the normal stress as well as the shear stress, is positive or negative. So the first concept lies over here. On the positive planes, if the stress component is in the positive coordinate directions, it will be termed as the positive stress. And the second concept is, on the negative planes, if the stress component is in the negative coordinate direction, it will again will be called as the positive stresses, and the things would be entirely opposite in the context of the negative shear stresses or the negative stresses, both in terms of the normal stresses and the shear stresses. Again, what is represented by the first row, it represents the forces that are acting on this particular plane, on positive planes. The second row represents the stresses that are acting on this particular plane, which is represented by 2, 7, 6 and 3. Again, this row this row represents all the stresses that are acting on the plane 3, 4, 5 and 6. So in general, three-dimensional state of stress, if we are interested in defining the stress at a particular point, how many components we need? We need a total of 9 components to define the state of stress at a particular point. Now we will do an example, numerical example to show the different state of the stress. The stress matrix is given by sigma xx, tau xy, tau xz, tau yx, tau yy, tau yz, tau zx, tau zy, and tau and sigma zz. Now we are interested in finding out, or we have to define the direction in which these values of stresses are acting. So the first values of which is given by sigma xs, this value is termed as minus 50. This means it would be acting perpendicular to the surface, which to a plane, that is this plane, and it would be pointing in the negative x directions. Why negative x directions? Because the values over here is given by the negative signs. Again, the values of sigma, again the values of tau xy is given as 30. So again it will be acting in the positive directions, and the values is given by values of tau xz is given by 10, which is this values, again this is acting in the positive directions because it is given by the positive signs. Again, if we move to the next row, we find that the different values of the stresses are given, which is given by tau yx, tau sigma x, sigma yy and tau yz. Different values are given. In this case, sigma yy, which is the normal stress, is given by the negative values. This means it will be acting in the negative y direction, which is shown over here, which is sigma yy. It is acting in the negative direction. That why it is given with a negative value. Instead of this, if I say that the values is positive, instead of giving the values minus 40, if I give it a values as 40, then in that case sigma yy would be acting in the opposite direction. It will be acting in this direction. Then it is will be termed as the positive directions of the normal stresses. Now the stresses represented by the third row, which are the stresses acting on the z plane. So this one is the z plane in the z directions. So in this case, the values of the tau zx is given by a value of 10, so it is acting in the positive direction because it is acting along the positive x directions. The values tau, zy, again this is acting in the positive y direction, so it will be termed as positive. Again the values of sigma zz, which is the normal stress, is acting in the positive z direction, so it will be termed as a value which is tensile and it is acting in the positive z directions. Again the next problem statement is, in this case we have to show the non-zero stress component on the different surfaces. The different surfaces are A, B and C of the two cubes which are given to you, cube 1 and cube 2. So this one is cube 1 and the other cube which is given is cube 2, shown in the different coordinate systems. So in this case the different coordinate systems are reversed. So in this case again we have to define or represent the different state of the stresses acting on the two different cubes, cube 1 and cube 2. So the different state of the stresses are given over here. We have to represent it on the different faces. If we consider the face C, the values that are acting on this particular phase is 80, which is the normal stresses. Again the values of 30, which is the shear stresses that is acting in this directions. And again the values of minus 70, which is again the shearing stress that is acting in the z directions. When we move to the second row, the various values of the stresses that are acting is the only one values of the shearing stress that is acting at the point B. So it is denoted by 30, which is acting in the positive x directions. There is no values of the normal stresses on the y plane and no values of the shearing stress on the y plane. Next, when we move to the third row, we have the forces that are acting on the z plane, which is z plane. Z plane is constant over here. The various forces that are acting on the z plane in the different directions. Over here, we have the values of the normal stresses, that is minus 40. That's why it is in this directions. The other values of the shearing stress that is acting is in this direction, as it is minus, so that's why it is acting in this direction. If it has to be positive, it would be acting in the other directions. And there is no values of the shearing stresses along the y direction, so we haven't represented it, and this value is 0. Again, for the second cube, we have to define the various non-zero stresses that are acting corresponding to the stress given by the 3 by 3 matrix. Again, the values of the stresses that are acting at the point A is the value represented by 80, 30 and minus 70s. So the values of the normal stresses is 80 and the values of the shearing stresses are 30 and 70. For the phase B, we have only one values of the shearing stresses that is acting in the positive directions. That's why here, over here, it represents the values only 30. The other values 0 and 0. The normal stresses that is acting on the y plane is 0 and the shearing stresses that is acting on the y plane is also 0, that is directed in the z direction. So we haven't represented the other forces. The next would be the third row, which is represents the forces that are acting on the z plane. So these are the z planes and the various forces that are acting in the different directions, x directions, y directions and z direction. So in this case The figure point denoted by point C represents the forces that are acting on this particular Z planes. So the values of the shearing stresses is minus 70. That's why it is acting in this directions. The values of the shearing stress over here is 0, so it has not been shown, and the values of the normal stresses that is acting on this particular plane is represented by minus 40. That's why it is acting in the negative Z directions. Now we will define the general state of the stress. When we represent, we have the stresses in two-dimensional, so it represents the two-dimensional state of the stress. In two-dimensional state of the stress, all the forces that are acting in the Z planes, so this column and this row will be 0, and we are left with only the four values of the stresses that are acting among these two forces. Among these forces, two values 80 and 40 are the normal stresses, and 30 represents the shearing stresses. As the shearing stresses are complementary to each other, that's why in order to define the stress at a particular point in two-dimensional figure, we need only three quantities. Two will be the normal stresses acting along the two perpendicular directions, and one will be the shearing stresses. As shearing stresses are complementary, so to define the stress in 2D, we need two values of the normal stresses and one values of the shearing stresses. As all the forces that are acting in the along the Z planes is 0, there won't be any values of the forces in the Z directions. So in this case, sigma yy, sigma yx, tau yx is the first one is the normal stress, second one is the shearing stress. The other values are the sigma xx, which is acting in the x directions, and tau xy, which is acting in the positive y direction. So these arrows represents the directions of the forces that are acting. These forces are the normal and the shearing stresses. Here the values of the sigma xx is 80, so this values is 80. Tau xy is the shearing stress acting on the x plane directed in the y directions. This value is 30. Again the forces that are acting in the y plane, so this one is the y plane. The values of the shearing stress, that is tau yx. Y represents the directions of the plane normal and x represents the directions of the stress. It is 30, and the values of the normal stress, which is represented by sigma yy, it is 40. So the learning outcome for this sessions would be, we have came through the general stress notations in a three-dimensional state of the stress. We came to know, or we understood the definitions of the normal stresses and the shearing stresses. How do we define when we call these values are positive and when we will call these values are negative. We have done an example to demonstrate how the orientations of the axis defines the different state of the stresses. Thereafter, we move to the general state of the stress that is acting in the two-dimensional. In the two-dimensional state of the stress, no stresses will be acting on the Z plane. So we are left with only four quantities. Among those four quantities, two will be the normal stresses and the other one will be the shearing stresses. So in two-dimensional figure, we need only three values of the stresses to define the stress at a particular point, because the other stress, which is the complementary shear stress, are same. That's all for this session. We will meet you in the next session. Thank you.